Okay, I think we're about ready to restart. I think just to summarize, just for my own benefit as well, what we got up to in the last session, we we used a dataset class to process our data and get it into a suitable format for PyTorch to understand. We instantiated our data loaders, train and valid data loaders, and the next step is to create our neural network, define our loss function, and do our training loops. So as I said, what we need in a neural network is our data processing, a loss function, an optimizer, and a model. And the next step is to do a model. Okay, so I think last session I was explaining to you how not to do it. I think I'll go through now how I would advise people to define their networks. And there's this really nice class which you can use, which is called from Torch. It's called from torch.nn imports sequential. And this is basically allows you to basically just daisy chain layers together. So I'll just show you how that's done. As I said previously, all of the architecture goes into this in the init initialization function. Sequential. I'm going to hard code these for now just to illustrate the dimensions of the neural network. And we finish off by providing a prediction that's in the same dimension as our one hot encoded vector, or the number of species, and that's 3.
So the sequential in the self.forward lab is basically, it will tell the model that this is how the data will flow in the model in the same sequence as you're defining them here.
Sorry, I'll come back in a minute. So I declared feats here. So what we need to be able to do is also provide these in feats and out feats. I've hard coded it at the moment. That's not ideal, but let's just do that. We've got and then target names. And one way of getting the target names is by doing something like this. So we define the data at the start, and we just the unique number of species. So is everyone sort of following that? Yep. Yes. Well, that's all done. That's all kind of inferred based on how you construct the network. We don't have to explicitly provide that as an input to that. It's just automatically built through some PyTorch magic. Perhaps, but I don't know why you would want to. But I could be wrong. Okay, so I'm just passing the in feats and the out feats. I'm probably going to get an error. I do. Okay. Okay, so you can print the model and you can see that it's built this architecture with a linear layer followed by your activation function, which we choose to be a ReLU. There are lots of different activations to choose from. You can go into the PyTorch documentation and look at what's available. So ReLU, leaky ReLU, sigmoid, etc. People seem to be using ReLU nowadays. That seems to be the most sort of stable activation function to use, and it speeds up training. I don't know why that works. It's a bit of a black art, but the state of the art, I think, is the leaky ReLU function. But let's have a look at what these. So it's very simple. It just sets all of the negative inputs to 0 and chooses the positive inputs, or selects the positive inputs. Okay. And just to test that this works, we can run the forward pass with a random input, so a 5x5 tensor, and we get something that looks reasonably sensible. And you'll notice that this grad function has been activated. Whenever you define your PyTorch neural network, it automatically turns on gradient tracking. So you can run back propagation on this. So something I'll talk about a bit more later. So is everyone following that so far? Still typing. So I've just created a very simple tensor which just shows that my forward pass works. So it's a 5x5 tensor. It's not important. You don't need to write this down. It's just just to see that it works. Yeah, exactly. And because of this callable thing that I was mentioning earlier, it automatically calls the forward pass. So it automatically does dot forward on that model. Yeah. So I've chosen 5. So what's this? It can be 1. It can be 1, 5. Yeah, it has to be 5. Yeah, that corresponds to the number of features exactly. Yeah. And that error is if I said it's 3, because 1 by 3 does not multiply 5 by 16. Okay, am I okay to move on? Yep. Right, so the next step is to select a loss function. This is quite straightforward, just loss equals BCE loss. Oh, I should say actually, maybe what might be interesting to look at is an actual model that, like a larger model, what that looks like. I can't remember how to define it. So yeah, just have a look at. So this isn't necessary for you to copy. We're not going to be using this code, but so ResNet, which is used for many computer vision problems, we can actually just inspect what the weights might look like from a trained model, if I can spell weights. Call ResNet 50 on this. Okay, so this is a much more complicated model with lots of convolution layers, pooling layers. Yeah. And you can even look at the parameters as well. So, because this is a trained model that's provided to people to use from, and then fine tune to their problems.
Yeah, so if you want, you don't have to define your own model every time. You can use the predefined ones as well that are available in Torch.
Oh yeah, I'm just, for some reason I'm doing the same thing again. Yeah, so you just call parameters on that. It gives you the values of all of the weights within that network, of which there are many. Well, it's probably a larger dimensional tensor. But. Okay, so that's just a bit of a digression. Don't worry too much about this code. Just a bit of illustration that you can look at other models, you can import them, you can use them for your own purposes. Okay, so we define our model. The next step is to select a loss function, which we're using as binary cross entropy. Have a look at what that is. It's a standard loss function for classification problems. I'm not going to go through the maths. There's some other things that might be worth mentioning, but at each step, you can choose whether to, if reduction is set to mean, you take the mean over the entire batch size, or you sum over the batch size. Just some crucial details to think about. I've never really encountered any issues with this in practice, but it's good to know by looking at the documentation. Okay, so next thing we do is use an optimizer. Yeah, I don't know. Ultimately, I think it's something just to be aware of in your problems. That I think the documentation goes into, for autoencoders in particular, that's applicable. I don't know the theory. There's probably a paper on this that you can read, which goes into this in detail. What the default is, yeah, the default's mean anyway. We take the mean over the batch, a loss of the batch. Okay, so optimizer is we're going to use the Adam optimizer. This is I've done something wrong. Yeah, thank you. Yeah, so this is telling the optimizer which three parameters in the model that we want to train. As we were just showing for this bigger model here, it's calling parameters on it. Everyone seems to be using Adam nowadays. You can use SGD, like the simple variant. Adam comes with some additional kind of I don't know what Adam does. Adam does some fancy stuff. There's a paper on it if you want to read more. PyTorch provides documentation. There's weight decay, and yeah, if you want to learn more, read the paper. Okay, so the next task is to write a basic training and validation loop. So we're basically going to take everything that we've defined so far, so the loss, the optimizer, the data, and the data loader, and the model. So we need to define an activation function. We're going to use softmax for this. So yeah, at the moment the neural network is predicting some values for our inputs, but these do not currently match with our targets. So they're not in like they're in the right dimension, which is 1 by 3, but they're not scaled between 0 and 1. So we need to scale the outputs. Softmax is a generalization of the sigmoid function to multiple dimensions. Yeah, you can read about it here. It's very similar. I mean, if people have studied physics, it's quite similar to the partition function in thermodynamics. And it's really good when the result is one of a set of things, so A, B, or C. It's really bad if you want to assign two classifications to a problem. So if you've got an image of a cat and a dog, and you want to be able to both classify the image as cat and dog, it's really bad. Don't use it. And be careful when I talk about, so it gives you some value between 0 and 1. Don't interpret this as a probability. It's not really a probability. It's more of a proxy for that. So it's not really statistical in the sense of probabilities in other methods like Gaussian processors and that are built from the ground up with statistics in mind. So if you want to have a go, we've got like 5-10 minutes just to have a go at writing one of these loops. I've given you some basically comments about what needs to be done in these at each step. So yeah, I'll start with setting up the model for training, then move on to this, and then we can worry about how to capture our metrics afterwards. I could do it for maybe I could do it for the train loader first, and then leave you to do the validation. But yeah. Well, a bit of a digression on tensors. I didn't really talk about this before, but so as I mentioned before, this requires grad is really important. It's basically telling the model to remember all the gradients as we train. You can set this explicitly using this required grad. So you want to see how this works. You'll see that these values have been raised to an exponent. It's captured that we've multiplied the vector by 2. So I'll probably just fill this in for you. So the first step is to model.train. This gets it all set up for training, and it's a really important part of training a network, because when this is enabled, certain layers behave differently compared to validation. So I think batch norm kind of turns on, which we haven't defined yet, but we will, and dropout layers kind of activate and things like that. So this is a really important part of it. For the validation loop, we also need to do model.eval. So this is something that a lot of researchers have forgotten about, and papers have been retracted over this because what we want at validation or evaluation phase, we want to be able to take the statistics that we've learned from the training step, not from the actual test set or the validation set. So if you drink statistics from the validation set, it's going to perform anomalously well. So yeah, you need to ensure that it's using the things that it's learned from the training guide. Is that all clear?
Basically, there are certain things like, dropout layers, batch normalization. All these things you require in the training bit, but not in the validation bit. So that is why we usually use model.train for training the model and model.eval for validating the model. Because model.eval will certainly skip some of the steps that are usually done in training but are not required in validation.
So we're looping over our train loader as we did before. The first step is to set the optimizer to 0 the gradients. So the reason we do that is that Torch sums the gradients automatically on each iteration. This is good for certain models, but for what we're doing, we want to be able to reinitialize all the gradients to 0 on each step so that it learns afresh.
So like saving this gradient thing is useful when you're trying to build physics-informed neural networks, because there you would require these values, but otherwise you can just turn them off.
Set that. Make sure that I've actually declared my optimizer there. Okay. Then we run the forward model, which I've showed you before. So we run the forward model on the batch. And as I said, we need to compute these proxy probabilities, and we do that by calling the softmax function, which you can just call on the tensor. And we need to ensure that this is done on the right dimension, which is the column dimension. So as I said before, we've got like a 16 by 3, and we want to ensure that the columns all sum to 1. So we'll get something. Our prediction will look something like this, 0.2, 0.7, 0.1, and we want to compare to the target. So the way we do that is by computing the loss. Well, we need to compute the loss, which is done by loss predicts reds and targets. Then we compute the gradients by calling the step function on the optimizer. I keep calling that wrong, sorry. Optim. And then, to compute the gradients, we actually call backwards, sorry. And then we nudge the parameters in the direction of steepest descent. Okay, does that all sort of make sense? Sorry, that's just my VS Code getting confused that I haven't spelled optimizer right. Yeah. No. Yeah.
You don't necessarily have to, but in case your application requires it, for example, like physics-informed neural networks,
Concept of said when the forward pass runs, it kind of computes this computational graph. And then all of the tensors, the fundamental building block of PyTorch, kind of stores all of these operations in a graph. And when you run backward, it kind of goes through it the backward way and kind of computes the gradients using chain rule. Right, okay. Yeah, thank you. This stuff isn't easy. People make mistakes. Thanks for capturing that. Okay, so is everyone clear on that? So the next thing to do is we need to capture our metrics, so our accuracy and our loss. So to do that, we'll store them in a dictionary. Dictionary of lists. And at each step, we append the batch level statistics. So we loss dot append, that's the item, and then metrics accuracy dot append. We need to define this function get accuracy, which we'll do in a minute, which takes the predictions and the targets. Okay. And this is just getting the loss value. We need to call item on that. It gives you a 1-by-1 tensor, and we append that to the metrics dictionary. Okay, is everyone okay so far? Yep. Yeah. Oh, sorry. Okay, so so we're looping over our train loader, which we've defined before. So let's just show you that. Yeah, so we're getting our batch. We're doing this on a batch basis, so we're getting tensors of dimension 16 by 5, where 5 is the number of features. Yep, and we have our targets, which are the same batch size, but with dimension 3. So we've got 0, 0, 1, or 0, 1, 0, or whatever, depending on the species. Yes, penguins' physical features.
So like whatever records you have, all the observations, they're divided into chunks. Those chunks are called batches.
Is the rest of it clear? Or so we zero the optimizer because we need to start from 0, ground 0. Our gradients are initialized to 0. We make a prediction, which is calling the model, calling the forward pass of the model. So over the batch, so we get some predictions. We compare the predictions to the targets. Yeah. So that will give you a prediction vector, which is, so ignore the batch for a second, but it will give you a prediction vector which would be of size 3. But the values in that don't have chalk, but the values in that vector won't necessarily sum to 1. And yeah, so we have different probabilities that, yeah. Exactly. Yeah. Sorry. Yeah. So it will give you some vector probabilities. There'll be something like this. Well, it won't be like this initially, but what we want it to be is something like this. So 0.2, 0.7. Obviously, you can't have 0.2 of one penguin and 0.7 of another. But so yeah, is everyone else following? Is that all okay? Yep. Yep. No. I think it's, yeah. Yeah. So yeah, so the neural network will be invariant to the batch size, and the batch is passed as a parameter here. So it expects a batch as some, which is a type of tensor. Will be batch, yeah, the batch dimension. Exactly, yeah, and that's why we have that's why the first linear layer has to be the same dimension as the number of features. Right, so I'm sure I'm going to introduce a bug somewhere. So I need to define this function called get accuracy, which I can do. Takes predicts targets, and I've forgotten how this works. So we need to make a decision, which is we call argmax on the prediction that we've got. So we're basically we're converting this 0.2, 0.7, 0.1 vector, and we're just getting it to tell us what is the most likely by the maximum argument. So we've already got our predictions from calling the forward model. We get the loss function, and then, so all of the training loops essentially done. We just need to capture all of our metrics. So how is the loss performing, and yeah, and what the accuracy of the model is. I mean here. So that computes our gradient. So we need to update the model by comparing the output of our predictions to our targets. So they are stored. It's not critical to know how they are, but PyTorch keeps track of all the gradients through this concept of a computational graph. So we don't have to actually explicitly pass the gradients into. It is a bit confusing, I agree, but you don't actually have to pass all of these gradients between all of the different functions. It's all captured behind the scenes. Yeah, it makes the API a lot simpler. Yeah, it's all magic. It makes it a lot simpler to do. Otherwise, you're having to track variable names and just accept that there's a computational graph that's created, and all of these gradients are sort of are computed by doing, well, all of these operations are kind of captured in this large computational graph. And yeah. So yeah, it's defined when you create your model and you run forward on it. So when you run, the first time you run forward on the model, it computes this computational graph. No, it's fine. No, it's good. These are good questions. So the optimizer basically nudges your parameters in the direction of steepest descent. So you've got these gradients, and now you want to nudge them in a certain direction. That, no,
sensitivity kind of objects.
they're not. In a sense, it looks like that, but
Somewhere magic.
somewhere magic, computational graph. I'm conscious of the time. Sorry, no, these are really good questions. Thank you. But yeah, it's kind of how I was illustrating it previously with this kind of example here, where you've got like a series of ones, and you turn requires grad on equals true, and it constructs this graph where as operations are applied to it. So you can think of the as you define the architecture, you define all these linear layers. These are just doing matrix operations, and you're building up these series of operations in a graph. Yeah. Yes.
It all goes in the background.
Okay. Right. So I need to define it to get the accuracy. And we do the same for the target. A bit of a both, but we get to max. Our target is a vector of 3 of size 3, has 0, 0, 1, and it just we want to get the index where that is maximum. You compare the decision to the target, and I think that's about it. Oh yeah, thank you. Oh yeah, thank you. So because this is operating over the batch level, these are actually tensors of size batch times sorry, they're of size batch times the number of classes, so 3. We need to average over this. So don't worry too much about this. It's quite succinct code, but I could have done it. Maybe if I do it next time, I'll do it a bit more verbose, so that it's clearer. So we convert these to floats, and then we take the mean. So we're getting the batch level mean on each step. Sorry? Yes, I do. Thank you. Oh, cheers. And now that's called and added to the metrics dictionary. Okay, we have 15 minutes to train a network. And at each step, we return a dictionary by taking the mean of the batch. So for each epoch, we basically take the mean over all of the batches. So this is just a bit of dictionary comprehension. And I need to do, so I'll come back to it in a second. Got the mean function from NumPy. So we're taking I can illustrate this with an example, but I'll just let people finish typing. It's a list, yeah. These are lists. It's a dictionary of type, string, and list, type list. Yeah. Okay. Right. So the next step is to do the same for the validation. Fine. It's a lot simpler this time. Let's call a forward model on the batch. Again, it's a bit of code duplication, but I don't think you do this. It's not good production code, but for the purposes of this exercise, it's fine. Sorry. Metrics again. Validation loader. Okay, is everyone okay with that? Okay, so to train, we basically run over these. We run over each epoch. Yeah. And that's one, sorry. An epoch, I should have explained, sorry. It's seeing the entirety of the data set once. So we've kind of chunked the data set into little batches here, so 16 element tensors, 16 by the number of features. And we're basically just going over these tensors, these batches, one after another, like that. Does that all make sense? We can talk more. We can talk more about it later. Yeah. So if you don't get everything like now, we do have the solutions online. So. All okay? Can I move on? Okay, so we just loop over each epoch repeatedly. So the model has to see the data many times in order to get good at fitting the function. So we define some train metrics again for the entire epoch. Append to it, train metrics dot append train dot. let's keep this cell. Okay, this might completely fail. We'll see. It does. Okay, I added an S by accident at this point, so. Validate on you, yeah. Yeah, I made a few mistakes. That's now training. So I made a few mistakes. I accidentally defined a function within another function. So where you have get accuracy in train one epoch, you need to move it out. And I called the optimizer here. What did I do? I added an S where I wasn't meant to, and I can't remember where that was. But is everyone kind of vaguely following? Yep. So does everyone have a training loop that works? Or people have no idea what's going on? Yep, it works. So we add these. We've added these metrics to the dictionary. And what's helpful is to convert these into pandas data frames. So metrics, data frame. And same for valid metrics. Sorry. Okay, so we're getting something that looks, it's a bit worrying because these values aren't changing, but it is calling the training loop, and there are a few things that we need to modify to the network in order for this to work. Is that all working for you? Do you? Yeah. So this. Is that the same for you, or? Okay.
Oh,
Can you show the error?
yeah.
Say that again, sorry?
Also,
This isn't
can you print your
this isn't good right now. So there are a few things that we need to change to the network to make this work.
eye condition.
Yeah, cool.
Thank you.
Oh, friends.
So one
Reds, yeah.
one thing that we should probably do is add some batch normalization layers to our inputs for our network. We can do.
I've got 3 input features.
Have you modified the way you have defined your neural net? Because the linear layer then needs to have like the number of layers there is going to be the same as the number of features that you're using. Input features 2?
Yeah, I have
Output 16?
So input features 2.
You said you're using 3.
Oh, did I say 3? Well, it should be detecting it. It should be figuring it out itself. Yeah, because when I do forward, it does work. So yeah, I must have just have 2 as the input, and then the predictions are 3, which is correct, right?
I'm getting it.
Yeah, it's definitely like running the forward pass okay, right?
Mm-hmm.
But it's just always predicting the first one.
Okay. I've added some batch norm layers to the network. I'll go back. So now in the network with something a bit like this, and the result should in theory be a bit better.
So I guess yeah, it is here, right? So it needs to be threads and targets. Presumably it's like how I've defined it. Example.
Yeah, I think maybe we can do that after the session.
Yeah.
Oh, okay. Maybe I should have done that instead.
Good work.
That's better. Okay, so is everyone following, or people got issues, or? So we're defining the accuracy metric. So the accuracy basically determines how well we're matching our target variables. So isn't getting better. This should be getting better, but it's not. My network isn't getting any better. Yeah, it should be getting close to 1. Yeah. I probably. Oh, hang on a sec. Well, that's just for. Yeah. But it should be increasing. But. We have a problem with our network. It's just not getting any better. But this is expected.
That sometimes happens.
Yeah, it sometimes happens. It's all there. It's just not working.
Yeah. We can.
Yeah.
Yeah, as we're getting into lunchtime.
Yeah, absolutely.
Yeah. So,
Yeah.
yeah.
Okay.
3 minutes.
So the conclusion is that this doesn't train very well, and I've introduced an error, and maybe as an exercise for you to try and determine what the error is that I've introduced, because this isn't straightforward. Mistakes are made. It's at least it's training. It's just not doing what we wanted it to do. So we do have to wrap up now and head over for lunch. So I'll be having lunch. So if anyone wants to ask me any questions, I'll be there. So thank you very much.
And just FYI, guys, the worked out solution is there in the repo. So you have something for your reference.